So in this process of reduction of H to triangular form, what you have to do, and this will be an important point for anyone who chooses to do the programming option for homework 4, is after each QR step, you have to monitor these subdiagonal entries. Of H. And if any of these entries are near 0, they basically will declare them to be 0. Then you have decoupling. And I've drawn this out before. So what happens is, in your matrix H, so here are your just your subdiagonal entries, and here's your upper triangular part. And I don't feel like doing that many X's. So if one of these entries, let's say this one, becomes 0, then the result of that is now you have this block and this block so you're not always working on the entire matrix. So initially, assuming your subdiagonal is totally non-zero, so unreduced Hessenberg matrix, you'll keep working on it until an entry, usually it's the last entry, but you never know. You have to check them all. It doesn't take much time to do that. As soon as n entry becomes 0, look for that opportunity to decouple, and then you can work on these diagonal blocks until all the diagonal blocks are whittled down to 1 by 1 or 2 by 2. So what do you have to do for each QR step? You have to apply the QR step to a maximal unreduced Hessenberg block. Again, for efficiency, you keep working on smaller and smaller matrices, so you keep finding the eigenvalues faster and faster once you get started. And I say maximal unreduced block because like doing something like working on this block would not be correct. You're leaving something out because the spectrum doesn't separate that way. So you can only work on blocks that are separated by 0 entries on the subdiagonal. And admittedly, the indexing can be kind of a pain to figure out, because you need to state which blocks you want to work on. And you can pick out one of these. Like I could say I'm going to work on the last block along the diagonal until it's down to 1 by 1 or 2 by 2, and then move on to the next block. It doesn't matter which order you do them in, as long as you're picking out blocks that really are really fit this block triangular structure. Okay. Right, so any questions about the Francis QR step? All right. Now, everything I've described is for finding eigenvalues of an unsymmetric matrix. When you have those eigenvalues using this QR algorithm, you do not have the eigenvectors. You have a sure decomposition. That can be used to get the eigenvectors, but and then you can find information on that, for instance, in Golub and Van Loom. It's a rather complicated method, though, and I won't get into it here. But if you're applying this to a normal matrix, then by getting a sure decomposition, you do get the eigenvectors. Right. But I want to make a quick comment about the symmetric case. jumping to chapter 8. Just a couple sections of that. On the symmetric problem. Now, the spectrum of A is real for a symmetric matrix. So you don't need this Francis QR step. It's overkill. You only need a single shift strategy. And the best strategy for that, now for the unsymmetric case, the single shift strategy is to use the n element. And you could use that. That's a very simple thing to do. It'll work, but a better choice is the Wilkinson shift. Now, there is a formula for Wilkinson shift in the notes, but I'll just explain the meaning of it. So it is the eigenvalue of this lower 2 by 2 block which is going to be symmetric, but I didn't really write it that way. That is closer to HNN. Now, a Hessenberg matrix, that's also symmetric, it's also tridiagonal, but that isn't really necessary for this discussion. Okay. So what you do is you just find the eigenvalues of this using quadratic formula, and then pick out the one that's closer to this entry. And what that means is this these off-diagonal entries go to 0 cubically. So if this entry is order epsilon, after you apply QR step, it'll be order epsilon cubed. So so that works out quite nicely. I want to give some computational costs of the whole process. Now, QR algorithm is an iterative method. You stop when it converges. You don't know how many iterations it's really going to need, but there are some guidelines that come from the knowledge that you can find an eigenvalue after just a few iterations due to quadratic convergence for the unsymmetric case and cubic convergence here. So I can give some very rough operation counts. Okay, first for the so for a single Francis QR step, that takes 10n squared operations. But to contrast, a symmetric QR step takes only 30n operations. The reason for the disparity is you're dealing with a tridiagonal matrix, so almost all of it is 0. So each Gibbons rotation takes less work. Okay, for the entire QR algorithm, again, these are rough because it's an iterative method, and there's a couple variables to consider. We have a case where it's unsymmetric or symmetric, and whether you want Q or no Q. And I mean, by Q or no Q, I mean, do you want the entire surety composition, or a Q, T, Q transpose? If you only want the eigenvalues, you don't want Q. But if you want to have a chance of getting the eigenvectors, then you do need to compute it. So for the unsymmetric case, we need 10n cubed floating point operations for the entire QR algorithm that's justified the eigenvalues. If you want Q, that adds a whole lot more overhead. So you're having to perform an extra 15n cubed operations. And then finally, for the symmetric eigenvalue problem, it only takes 4/3 n cubed, so only twice as long as Gaussian elimination, so that's quite nice. But then you have to add on, I don't feel like dealing with fractions now. Okay. Alright, want the eigenvectors as well. So I should mention for the unsymmetric case, if you want the eigenvectors, you need even more work beyond this, because you only have a sure decomposition. There's extra work to get the eigenvectors, whereas here, you have the eigenvectors once you have Q. Okay. So as you can see, the eigenvalue problem, especially for the unsymmetric case, is significantly more expensive than, say, Gaussian elimination. You're solving a system of equations that's 2/3 m cubed. But you're gathering a whole lot of vital information about the matrix that can be useful for other things. Okay. So the I function in MATLAB, they're basically